PhD student at Technion. Today I will present the study titled Generation of Acoustic Ontology for a Holistic Building Performance Domain. This study is a part of Cloud-Based Building Information Modeling (CBIM) project funding from European Union's Horizon 2020 research program. I want to start with a brief introduction. What is building performance domain? The building performance domain composes of a diverse set of performance aspects such as energy, air quality, acoustic, lighting, and so on. Therefore, the building performance domain has various application-specific data and heterogeneous data structures, which leads to poor interoperability and data integrity. Regarding interoperability, the current building information modeling BIM software is not able to perform acoustic simulation on a BIM model enriched with acoustical data. Also, the acoustic domain information is still application-specific, which brings a data integrity problem. Therefore, a building acoustic ontology with a generalized and integrated data structure is absent. Regarding data integrity concerns, ontologies have been proposed. Ontology provides the stored structures, also visualize knowledge of heterogeneous and decentralized systems. In addition, application-specific knowledge is represented in an abstract form in an ontology. Also, ontology can represent simulation intent. However, to date, there is no combined and comprehensive ontology in the building acoustic performance. Consequently, this study aims to design an acoustic ontology as a knowledge repository by storing the building acoustic principles in generalized conceptual modeling and combining semantics and object relations with the building information graph. While designing building acoustic ontology, we followed four steps method. The first step was the literature survey on the building acoustic principles. We found that the building acoustic principles strictly depend on the building geometry, physical objects, and sound source properties. The second step was the implementation of reverse engineering on building acoustic simulation software to understand the internal data schema. Therefore, we generated 3 conceptual models that represents the internal data schema of the acoustic simulation softwares. These concept models were generated in unified modeling language UML diagrams. The next step was the generalization of the semantics and object relationships among the concept models. The concept models were generalized in practical terms such as geometry, building objects, and object relationships. The identified generic semantics and relations were interpreted to communicate with the other building model ontologies. The last step is the transformation of the UML models into a building acoustic ontology. For that one, the UML classes, relationships, attributes, and cardinalities were converted to OEL classes, object properties, data properties, and the restrictions. Consequently, the building acoustic ontology was generated and linked with the building model ontologies. The design ontology is represented by blue color. After this point, I would like to mention the main concerns while designing this ontology. The one main concern was the combining acoustic ontology with existing building ontologies. Therefore, the main criteria for combining existing ontologies was to align the building's physical objects and topological relationships among them. As a result, the building model ontologies, which are building element ontology, distribution element ontology, building topological ontology, and CBIM ontology that represents interdomain topological relationships, were incorporated into the building acoustic ontology with their international resource identifiers. The linkage among the building model ontologies was achieved via functional object class in the acoustic ontology. The next concern was to represent domain functionalities in the acoustic ontology. Therefore, the functional class was generated, which refers to the acoustic functionalities of the physical objects. Functional object class has 3 subclasses, and each subclass has its own domain properties. For example, insulation material class has the properties of color, density, frequency, and absorption, and so on. Receiver class has mainly decibel frequencies, and sound source class has the properties like frequency, emission spectrum, and correction factor. The next concern was to represent object geometry information in the acoustic ontology. To represent the abstract level object geometry information in the building acoustic ontology, we generated 2 classes, which are abstract geometry and relative geometry classes. The geometry of the object is represented in the abstract geometry class with the bounding box, space boundary, surface, and 3D points. In addition, the positioning of the functional objects and/or physical objects is represented via the relative geometry class. The positioning information is represented as distance under the relative geometry class. The last concern was to provide building acoustic analysis results into the acoustic ontology. Therefore, target object class was generated, which refers to the analysis environment defined by the building physical objects. Also, simulation run class was generated to bind the use sound source from the functional object class with the linkage with its abstract geometry informations and simulation environment boundaries from the target object class with the linkage of also its abstract geometry information. Lastly, simulation result class was generated to store the outcomes of the analysis. Consequently, the building acoustic ontology was developed with 24 classes, 8 object properties, 58 data properties, and 313 axioms. To sum up, the contribution of the building acoustic ontology is in providing a knowledge domain guide by ascertaining, firstly, domain concept models, secondly, generalized semantic concepts and relationships among them, and also required information from different simulation software as well as unique concepts and information, and lastly, semantic links between the domain-specific objects and building models. Thank you for your attention.